So today I'm going to talk about infinite series, which is the sum of an infinite series actually. So this depends heavily on our discussion of sequences. So I hope you remember that everything we said about sequences, because a series is defined based on a sequence. So we said that you can have a sequence, which is basically an endless list of numbers like this: A1, A2, A3, A4, or in some cases you may start from A0, A1, A2, A3, A4, and so on. And there's also AN, which is called the general term of the sequence. Yes. So here you have an example of a sequence. And for this sequence, the general term AN is basically 2/3 to the power of n. And I can express this sequence like this. I put the general term 2/3 to the power of n inside curly brackets, and then I indicate where does n start. And for this particular example we have here, n starts at 0 and keeps on to infinity. So when n is 0, we get 2/3 to the power of 0, which is anything to the power of 0 is 1. And then we get 2/3 to the power of 1. That's 2/3. Then we get 2/3 to the power of 2, then 2/3 to the power of 3. And this continues like this. So this is a sequence. Now, if you add up all the terms of a sequence from the first one forever, what you get is called a series. So I'm going to use S to indicate the infinite series, and S is going to be A0 plus A1 plus A2 all the way to infinity. So this is an infinite series, which I can use, I can express using the summation notation. I can say, I can use I or K, doesn't matter. I think this book we are using N. Yeah. So N from 0 to infinity of the general term of the sequence 2/3 to the power of n. And when n is 0, I get the first term. Then when n is 1, I get the second one. Then it's 2, I get the third one. And summation, this is the sigma is the summation notation. So it means the sum of all these terms. So that would be our series, our infinite series. So each series is defined based on a sequence. Now, in order to study a series, we need to define some concepts and notations. So something like this that I indicated with S is called an infinite series, or simply a series. These A1, A2, A3, or A0, A1, A2, A3, these are called the terms of the series. AN, that is called the general term of the series. And you can use the summation notation like this to denote a series. Now, in order to study a series, we're going to introduce something called the sequence of partial sums. The sequence of partial sums. And we need this concept in order to be able to study sequences, series. So imagine you have this series, sigma n from 1 to infinity an, which has been defined based on the sequence an n from 1 to infinity. Now, using this sequence, you can create another sequence called the sequence of partial sum. And this is how you create that other sequence. That sequence has the form S1, S2, S3, S4, so on, Sn, and it goes like this forever, where S1 is simply A1. And S2 is the sum of A1 and A2. And S3 is the sum of A1, A2, and A3. And generally, Sn is the sum of the first n terms. So it's A1 plus A2 all the way to An. So as you can see here, we have a sequence. Yes, we have an endless list of numbers, S1, S2, S3, S4, all the way. And this sequence has been defined based on the original sequence that we had over here. It's called the sequence of partial sums. And this is how it's defined. So I can say the general term of this sequence, Sn, is basically sum of a k from 1 to n. So first I have A1, because k is 1, then I have A2, then I have A3, and all the way up to An. So did you understand the idea of the sequence of partial sums? So here you have the definition for the nth partial sum of an infinite series. Given an infinite series like this, sigma n from 1 to infinity An, that is A1 plus A2 plus A3 all the way forever, you can create something called the nth partial sum. And the nth partial sum, I use lowercase n, you can use uppercase n. Sn is going to be sigma An, n from 1 to uppercase n, that is A1 plus A2 plus A3 all the way to A uppercase n. Now, since this is a sequence, and we have already talked about the convergence of sequences, we know that we can take the limit of a sequence and see whether that sequence converges or diverges. So, for example, we can take the limit of An as n approaches infinity to see whether the sequence converges into a finite number or it diverges to infinity or negative infinity, or it just does not approach any limit. So since the sequence of partial sum is a sequence, you can do exact same thing. You can take the limit of Sn as n approaches infinity. Now, if this sequence of partial sums converges, in other words, if this limit over here, if that limit exists, then you would say that the infinite series converges. But if the sequence of partial sum does not converge into any finite number, you would say that the series diverges or is divergent. So if the sequence of partial sums, Sn, converges to a number S, that is, if the limit of Sn as n approaches infinity is some number S, then you would say that this infinite series converges and the sum is S. And you can just say that this series, which is A1 plus A2 plus A3 all the way, the sum of infinitely many terms is equal S. And otherwise, if this limit does not exist, if it's infinity minus infinity or simply does not exist, then you would say that the series is divergent. So everything will become more clear when we look at these examples here. Any questions so far? Okay. So imagine you have this series n from 1 to infinity, negative 1 to the power of n plus 1. So If I want to write down the general term of this series, that would be an is equal -1 to the power of n plus 1. So when n is 1, I'm going to get -1 to the power of 2. That's 1. So that's my a1, which is 1. Then n is 2. I get a2. That's going to be -1 because that's going to be -1 to the power of 3. Then I get 1. Then I get -1. And you see what happens here. So the sequence is going to look like this. Begins with a 1, then -1, then 1, then -1, then 1. It goes like this forever. So based on this sequence, with this general term here, if I want to create my sequence of partial sums, it's going to be like this. S1 is simply A1, so it's going to be 1. S2 is A1 plus A2. That's going to be the sum of the first two terms. It's going to be 0. Then S3 is going to be the sum of the first three terms, so A1 plus A2 plus A3. If I just add up these, I'm going to get 1. S4 is going to be A1 plus A2 plus A3 plus A4. It's going to be 0. So when I look at the sequence of partial sums, I see that this sequence, which has been defined based on my original sequence over here, the sequence of partial sums, has the form 1, 0, 1, 0, 1, 0, and so on. And this continues like this, the same pattern forever. So it's clear that if I take the limits of Sn as n approaches infinity, this limit does not exist because there is no single finite number that these values approach. There is no approaching here. The values just alternate between 1 and 0, 1 and 0. So this means that this limit here does not approach any finite number, thus it does not exist. And if this limit does not exist, this means that this series that we began with over here is divergent. So the series that we started studying here is divergent because the limit of the sequence of partial sum is divergent. That's exactly what is mentioned here. You create that sequence of partial sums and you study that sequence. If that sequence is convergent, then you say the series is convergent. And if that sequence is divergent, you say that the series is divergent. Are we good? Okay, so let's take a look at the next example. Show that the following infinite series converges. So we have sigma n from 1 to infinity of 1 over n times n plus 1. So this series is defined based on this sequence. 1 over n times n plus 1, where n starts at 1 and goes to infinity. So if I just write down the terms of the sequence, it's going to be 1 over 2, because I get 2 times 1, 1 over 2. Then the next value is going to be 1 over 2 times 3, 1 over 6. Then it's 1 over 3 times 4, so it's going to be 12. And it's going to be like this forever. And the general term, as indicated here, is 1 over n times n plus 1. So this is the sequence based on which this series has been built, has been defined. Now I can do a trick to show that, to create a formula for the for the sequence of partial sums. So if I just write it like this, if I say, okay, S1 is 1 over 2, what I did for the previous one. S2 is 1 over 2 plus 1 over 6. S3 is 1 over 2 plus 1 over 6 plus 1 over 12. And so on. If I do it like this, I wouldn't be able to find a formula for Sn. Or let's just use the notation that we have in the book, use uppercase N. I wouldn't be able to find a formula for Sn and then take the limit of Sn as n approaches infinity. Yes, not using this method. So what I'm going to do is I'm going to use the fact that this series here is a telescoping series. And I will show you in a bit what I mean by a telescoping series. So let me just keep whatever I have here. I may need to refer to that. Okay, so far you see that if I am able to find a formula for Sn, then I will be able to take the limit of Sn as n approaches infinity. And that's the goal here. I'm trying to find a formula for the general term of the sequence of partial sums. Because if I have a formula for that, I'm done. I just take the limit of Sn as n approaches infinity. If this limit exists, then the sequence of partial sums is convergent, and thus the series is convergent. So, we learned about this technique. If I have 1 over n times n plus 1, I can write that as a over n plus b over n plus 1. Yes, partial fractions, the technique that we use in order to solve integrals. And then we would say, okay, so 1 is equal a times n plus 1 plus b times n. I can plug in 0 for n. If n is 0, then I get 1 over 2 for a, because 1 is going to be a plus 0. So no, a is going to be exactly just 1. And if n is 1, that means 1 is equal, or if I plug in -1, that would be easier. That gives me b. So that's going to be 0. It's going to be negative b. That means b itself is going to be -1. So I can write 1 over n times n plus 1 as 1 over n minus 1 over n plus 1. So these are equal. So the series that I have here, sigma 1 over n plus 1, n from 1 to infinity, that's the same as having sigma n from 1 to infinity of 1 over n minus 1 over n plus 1. Right? So now if I write Sn, and Sn is the general term of the sequence of partial sums. So you can see that this is S1, which is going to be just A1, then S2, which is going to be A1 plus A2, S3, and all the way Sn. That would be the sum of the first n terms. Let's see what happens when, so this is going to be sigma 1 over n minus 1 over n plus 1. N changes from 1 to uppercase n. That's the sum of the first n terms of the sequence. So if I do that, I'm going to get this. I'm going to get, when n is 1, I get 1 minus 1 over 2 plus. When n is 2, I get 1 over 2 minus 1 over 3 plus all the way up to the last one, where I get 1 over n, uppercase n, minus 1 over uppercase n plus 1. It's going to be like that. So I'm going to use the book from here on. Sn, which is the general term for the sequence of partial sums is going to be the first n terms of the sequence, the sum of the first n terms of the sequence, and I just expand it. I write the values. When I plug in 1, I get this, plus plug in 2, I get this, and when I plug in uppercase N, I get this. Okay, now look what happens now. I have a minus 1 over 2 and I have a plus 1 over 2. I have a minus 1 over 3 and I have a plus 1 over 3. I have a minus 1 over 4, and in the next term, I'm going to have a plus 1 over 4. And you can see that these things all cancel out, and the only terms that are left are going to be the first one here, and the last one, negative 1 over n plus 1. So this collapses into just simple term 1 minus 1 over n plus 1. So I was able to find a formula for Sn. Sn turns out to be 1 minus 1 over n plus 1. And I can now easily take the limit of Sn as n approaches infinity and see what happens. And it's evident that if n approaches infinity, this part is going to approach 0, so this is going to be equal 1. That means the sequence of partial sums is convergent to 1, then automatically the series is convergent and it converges to 1. This series is equal 1. That is, if you just add up all these numbers, if you add up 1 over 2 plus 1 over 6 plus 1 over 12, the same pattern forever to infinity, you get 1. Make sense? Any questions? Okay, so basically we're going to look at two types of series in this section of the book. One of them is called geometric series, and the other one is called telescoping series. And the one that I showed you was an example of a telescoping series. I'm going to give you one more example of a telescoping series before talking about geometric series. And this is the only two types of series that you need to worry about in this course. In this section, not in this course, in this section. In the next section, we're going to look at other types. But in this section, these are the only two that you need to worry about. So let me just go to the exercises and find the telescoping series and solve it. Okay. So for example, if you look at number 4, that's the telescoping series. You have n from 2 to infinity of 1 over ln of n minus 1 over ln of n plus 1. And it's obvious it's telescoping because of this format that it has, but sometimes it's not obvious, like the example I just did, or number 3, it's not very obvious that this is telescoping. But if you factor the denominator, you will see that there are two factors in the denominator, n plus 1 and n plus 2. And when you use the technique of partial fractions, you can write it as a over n plus 1 minus b over n plus 2, and a turns out to be 1, b turns out to be minus 1. So this is, number 3 is very similar to the one that I just did. And number 4, because of the format, you can see that it's telescoping. Now, let me try to write Sn. Sn is the sum of the first n terms of the sequence. So that's going to be sum n from 2 to uppercase n. And it's going to be like this. First n is 2, 1 over ln of n minus 1 over ln of n plus 1. So when n is 2, I'm going to get 1 over ln of 2 minus 1 over ln of 3 plus. Then the second term is going to be when n is 3. 1 over ln of 3 minus 1 over ln of 4. And this continues up to when n is uppercase n. So I get 1 over ln of uppercase n minus 1 over ln of uppercase n plus 1. And you can see what happens here. This cancels this. This one will be canceled with the next term. And this will be canceled with the term prior to that. So it will end up to be 1 over ln of 2 minus 1 over ln of uppercase n plus 1. And now, if I take the limit of Sn as n approaches infinity, you see this part here is going to be 0 because ln of infinity is infinity. 1 over infinity is 0. So I get 1 over ln of 2. That means this series here is equal 1 over ln of 2. It is convergent, and it converges to 1 over ln of 2. Any questions about telescoping series? Yes?
I have a question.
Go ahead.
How do you know that it's the 1 over ln of capital N that you have to like cross out?
How do you know that this is the one that I have to cross out?
Yeah.
Because you know you can
one?
because of the pattern. Look, in the first one, the first term cannot be canceled, but the second term is canceled with the one right after that. Then this one is canceled with the one right after that. That means this one would be canceled with the one right before it.
Oh yeah, that makes sense. Yeah. Okay, thank you.
Another way of seeing this obviously is that you write it for n equal 2, then n equal 3. Then you also write it for the case where n is equal uppercase n minus 1. So you write the term right before the last term. And then you will see that this gets canceled with negative 1 over ln of n.
All right. Thank you.
Sure. Okay, so now let's take a look at a geometric series. So that's the other type of series for which you will be able to find a formula for Sn. A geometric series is a series that has been built on a sequence like this. So if you have A, which is called the initial term, then AR, then AR squared, then AR to the power of 3, and so on. So this sequence here is called the geometric sequence. And if you have a series that has been built on a geometric sequence, is going to be called it's called the geometric series. Now, A is the initial term, and R is called the common ratio. The example that I gave you at the beginning was a geometric sequence. So if you have 1, then you have 2 over 3 to the power of 1, then you have 2 over 3 to the power of 2, then you have 2 over 3 to the power of 3. So in this case, A is just 1, and R, which is the common ratio, is 2 over 3. And you can see that this follows this pattern here. 1, then 2 over 3 to the power of 1. So 1 times 2 over 3. Then 1 times 2 over 3 to the power of 2. Then 1 times 2 over 3 to the power of 3, and so on. So if you add up all the terms of a geometric sequence like this, what you get is a geometric series. So a geometric series is going to have the form sigma n from 0 to infinity a r to the power of n. When n is 0, you get a, because r to the power of 0 is going to be 1. Then you get ar, then you get ar squared, and this continues forever. And for such a series, you will be able to find the formula for Sn. And it's very easy. I'm going to show you how. So if your sequence is geometric and your series has this form, ar to the power of n, then Sn, which is the sum of the first n terms of the series, is going to be a plus 8r plus ar squared, all the way to the nth one, which is going to be a r to the power of n. Now, if I multiply both sides of this, oops, I have to rewrite that. So ignore this, Sn, which is the general term of the sequence of partial sums. In other words, Sn is the sum of the first n terms of the series. It's going to be a, the first term, ar plus ar squared, all the way to ar to the power of n. Now, if I multiply both sides of this by r, what happens? On the left, I get r times Sn. On the right, I get r times this whole expression. I have to distribute that r. I have to multiply every one of these by r. I get ar plus ar squared plus ar to the power of 3, all the way to ar to the power of n plus 1. Right? Now, since this side is equal this side, and this side is equal this side, if I do this minus this, that's going to be the same as this minus this. So Sn minus r times Sn is going to be this expression here minus this expression. And look what happens if I do Sn minus r times Sn. AR here and the AR here will cancel out. Yes. AR squared here and AR squared here will also cancel out. And we will be left with only two terms. The A here, which does not have a counterpart here to cancel it. And also the last one. So we get minus AR to the power of n plus 1. So at this point, I can factor out Sn. 1 minus r is equal, I can here factor out a, 1 minus r to the power of n plus 1, and have a formula for Sn. A times 1 minus r to the power of n plus 1 over 1 minus r, dividing both sides by 1 minus r. I was able to find a formula for Sn. So now I can take the limit of that as n approaches infinity. And if that limit is a finite number, I can say this series is equal to that finite number. And if that limit is infinity or does not exist, then I would say that the series is divergent. So do we understand the calculations here? Very simple algebra. Just the trick is multiply both sides by r and then do Sn minus rsn. And then everything will get canceled except for a and minus a times r to the power of n plus 1. Factor out Sn, you factor out a, you isolate your Sn, you get a formula. And we figured out the formula is, so for the series r to the power of n from 0 to infinity, Sn, which is the general term for the sequence of partial sums, is a times 1 minus r to the power of n plus 1 over 1 minus r. Okay, now there is only one way that this limit will exist, the limit of Sn as n approaches infinity. And this limit will only exist if r is something between -1 and 1. So if r is something between -1 and 1, in other words, if absolute value of r is less than 1, then this is going to happen. As n approaches infinity, n plus 1 also approaches infinity. And a number that is between -1 and 1, if you raise it to the power of infinity, you're going to get 0. So think of, for example, a number between -1 and 1, like, for example, 1 over 2. What happens when you raise 1 over 2 to the power of 2, then 3, then 4, then 5? You get 1 over 2, then 1 over 4, then 1 over 8, then 1 over 16, then 1 over 32. It keeps getting smaller and smaller. If you have a number that's greater than 1, raising that to the power of infinity will give you infinity. This whole thing will become negative infinity then. Or if you have a number that's less than -1, the same thing will happen. A number that's less than -1, when you raise it to the power of infinity, it will be either infinity or minus infinity. So in those cases, the limit will not exist. But if r, your common ratio, so don't forget, r is called the common ratio. If your r is somewhere between -1 and 1, then this part, when n approaches infinity, is going to approach 0. And this will become just a over 1 minus r. And thus you have this theorem. If absolute value of r is less than 1, in other words, if r is somewhere between -1 and 1, it doesn't work for equal 1 or equal -1. It won't work for that. But as long as it's between -1 and 1, then this geometric series is going to converge to a over 1 minus r. And the moment r is 1 or -1 or anything greater than 1 or anything less than -1, the series will diverge. So in order to see and tell whether a series, a geometric series, is convergent or divergent, you only need to find a and r. The first term and the common ratio. That's it. If you see that your common ratio is between -1 and 1, then you know that the series converges into a over 1 minus r. Let's look at these examples. We have sigma 1 over n to the power of 2, n from 0 to infinity. So you can see that I can write this as sigma n from 0 to infinity of 1 times 1 over 2 to the power of n. Yes, I'm just trying to show you that this has the form sigma a times r to the power of n, n from 0 to infinity. So it is a geometric series where a is 1. That is, if I plug in 0 into this, I get 1 over 2 to the power of 0. That's 1 over 1. That's 1. And it's clear that the common ratio r is 1 over 2. And 1 over 2 is somewhere between -1 and 1. So this series converges to a over 1 minus r. It's going to be 1 over 1 over 2. It's going to be 2. Is that clear? Let's look at part B. We have sigma n from 0 to infinity of 3 times 5 over 2 to the power of n. I can see the first term of this sequence is going to be when I plug in 0 here, I get 5 over 2 to the power of 0. That's 1. 3 times 1, 3. So that's the first term, a equals 3. And the common ratio is clearly 5 over 2. And this is greater than 1. So this one diverges. You good? And part C, so this was part B, part C, I have sigma n from 1 to infinity 5 times negative 3 over 4 to the power of n. Okay, I can see that this is a geometric series and the common ratio is negative 3 over 4 because I have the part negative 3 over 4 to the power of n. And negative 3 over 4 is a number between negative 1 and 1. So this is going to be convergent. Now, let's find the first term. The first term is when I plug in 1 in the general term. So what happens if I plug in 1 into this? I get 5 times negative 3 over 4. That's going to be negative 15 over 4. So that's my A, the first term. What is the general, what is the common ratio? It's clear, it's negative 3 over 4. So I just need to plug in values into the formula a over 1 minus r. So this geometric series is going to be equal negative 15 over 4 over 1 minus 3 over 4. That's negative 15 over 4 over 7 over 4. That's going to be negative 15 over 7. Is that clear?
So it converges?
Yes, it converges to negative 15 over 7. That is, if you add up these terms from the first one up to infinity, the value of that sum is going to be equal negative 15 over 7.
Okay.
Yeah. Okay, so we can now go back to this example that this section begins with and see that this is a geometric sequence, and thus the series is going to be a geometric series. So the first term is 1, then you have 2 over 3, then you have 2 over 3 to the power of 2, and so on. So the series itself would be n from 0 to infinity, 2 over 3 to the power of n. So first n is 0, you get 2 over 3 to the power of 1, you get 1. Then it's 1, then 2, then 3. So a is 1. The common ratio is 2 over 3. And 2 over 3 is between negative 1 and 1. So this is going to be equal, S is going to be equal A over 1 minus R, which is 1 over 1 minus 2 over 3. That's 1 over 3. It's going to be equal 3. So if you just add up all these numbers, you get 3. So 1 plus 2 over 3 plus 2 over 3 to the power of 2 plus 2 over 3 to the power of 3 all the way to infinity. If you add them all up, you get 3. Okay, so yeah, here you have a different problem because your initial value is not 1, it's 4/3, and this will give you 5. But if you have this sequence here, and your series is based on this sequence, you're going to get 3. Now, a few properties of infinite series, and you have seen these properties for finite series. If you have a finite summation, we know that if you have a C, and that C is a value that does not depend on n, you can bring it out of the summation. So with infinite series, you still have the same property as long as the two series, sigma an and sigma bn, are convergent. So if sigma an and sigma bn are convergent and C is a constant, then you can just move this C out of the summation notation. It's like factoring out from an infinite sum. And sigma an plus bn is going to be sigma an plus sigma bn, and sigma an minus bn is going to be sigma an minus sigma bn, as long as these are convergent. So how does this help? This help you solve problems like this. Example 4. We're going to evaluate this infinite series, n from 0 to infinity, 2 times 3 to the power of n minus 2 to the power of n over 5 to the power of n. I'm going to write this as sigma n from 0 to infinity of 2 times 3 over 5 to the power of n minus 2 over 5 to the power of n. Is this clear so far? Because notice that I can write the general term as 2 times 3 to the power of n over 5 to the power of n minus 2 to the power of n over 5 to the power of n. But this part here is equal 3 over 5 to the power of n, and this is 2 over 5 to the power of n. So this becomes 2 times 3 over 5 to the power of n minus 2 over 5 to the power of n. And then I'm going to use, I can see that both of these are between -1 and 1. 3 over 5 is less than 1. 2 over 5 is also less than 1. So this is going to be the sum of sigma n from 0 to infinity of 2 times 3 over 5 to the power of n minus sigma 2 over 5 to the power of n from 0 to infinity. I'm using this property here with the minus. Now I can use the formula for geometric series. The first term of this is going to be 2. Imagine if I plug in 0 into this, I get 3 over 5 to the power of 0 is 1. 1 times 2, 2. Over 1 minus r, and r is 3 over 5. Minus, this series is going to start with 1. If I plug in 0 for n, I get 2 over 5 to the power of 0, that's 1. So the first term is 1, a is 1, minus 1 over 1 minus r, and r for this one is 2 over 5. So I would just need to simplify this, and that will give me the answer. So 2 times 1 over 1 minus 3 over 5 minus 1 over 1 minus 2 over 5. If you simplify that, you get 10 over 3. So you can just replace this 1 here with 5 over 5. this one here with 5 over 5, you get 2 over 5 minus 1 over 3 over 5. So this becomes 10 over 2 minus 5 over 3. Over 2 minus 5 over 3. If you use a calculator, you're going to get 10 over 3. Any questions?